Equations of planes. I want to start by looking at some special cases of planes, starting with the planes that are parallel to the coordinate planes. So, for example, here we have a picture of a plane that's parallel to the YZ plane. A plane that's parallel to the YZ plane has equation x equals a for some real number a. For example, the YZ plane itself has the equation x equals 0 because the x coordinate of every point in the YZ plane is 0. Similarly, if a is a positive number, then we have x equal a being the equation of a plane that's in front of the YZ plane. And if a is negative, then x equals a would be the equation of a plane that is parallel to the YZ plane but behind it. Similarly, planes with equation y equals b for some real number b will be parallel to the xz plane. The xz plane itself has equation y equals 0. And finally, planes with equation z equals c for some real number c are parallel to the xy plane. The xy plane has equation z equals 0 because the z coordinate of every point in the xy plane is 0. Let's look at planes in general now. A particularly nice form to write an equation of a plane in is the point normal form. This equation has the form a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0, where x0, y0, z0 is some point in the plane, and the vector ABC is normal to the plane. I'm going to give a derivation of this formula now. If you're not interested in seeing the derivation, then feel free to skip ahead. For those of you that would like to see where this formula comes from, I'm going to show you that now. Let's start with a picture of a plane. And let's take a point in that plane, x0, y0, z0, and we'll draw the given normal vector to the plane with the components a, b, and c, so that the initial point of the normal vector is x0, y0, z0. I'm also going to draw the vector with components x0, y0, z0 in standard position, and we'll name that vector r sub 0. Okay, now since the vector is in standard position, that means its initial point is at the origin, and its terminal point is the point x0, y0, z0. Let's take an arbitrary point in the plane with coordinates x, y, and z, and let's also draw the corresponding vector with components x, y, and z in standard position. Again, this means that the initial point of the vector is the origin, and the terminal point is x, y, z. Now, the trick to generating this equation is to draw the vector r minus r0. Remember that r minus r0 begins at the terminal point of r0 and ends at the terminal point of r. This vector is orthogonal to the normal vector because it lies inside the plane, and the normal vector is normal to the plane. It follows that the dot product of n with r minus r0 is 0. Writing that in component form, we have that the vector ABC and the vector x minus x0, y minus y0, z minus z0 have a dot product which is equal to 0. Now, if we just go ahead and take that dot product, we get a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. This is precisely the point normal form of the equation of the plane. Notice that I started with an arbitrary x, y, z in the plane, and we saw that this equation is satisfied. If we started with a point x, y, z not in the plane, then the corresponding r minus r0 would not be orthogonal to n, and therefore that point would not satisfy this equation. So we see that this equation is satisfied precisely and only by the points that are in the plane. Sometimes we'll also want to look at the general form for the equation of a plane. That's ax plus by plus cz plus d equals 0. We could get from point normal form to general form simply by distributing the a, b, and c, and then combining all the constants into one constant d. Notice that in general form, we could still see that the vector ABC is normal to the plane, but we lose information about a specific point in the plane. It's time for an example. As always, you should pause the video, try this example yourself, and then resume the video to check your answer with mine. Find an equation for the plane which contains the point 4, negative 1, 3, and is perpendicular to the vector n equals 2i plus 8j minus 5k. Okay, this question is perfectly set up for us to simply put our answer in point normal form. So we get 2 times x minus 4 plus 8 times y minus negative 1, or equivalently y plus 1, minus 5 times z minus 3 is equal to 0. Let's try another example. Again, pause the video and try it yourself first. Determine whether the planes 3x minus 4y plus 5z equals 0 and negative 6x plus 8y minus 10z minus 4 equals 0 are parallel. So two planes are parallel if and only if the normal vectors defining them are parallel. So we can simply check if the vectors 3, negative 4, 5 and negative 6, 8, negative 10 are parallel. Or in other words, are those vectors scalar multiples of each other? An easy way to check this is just to divide 3 by negative 6, negative 4 by 8, and 5 by negative 10, and see if we get the same answer. And since we do, then in fact, yes, these two planes are parallel because we just showed that the corresponding normal vectors are parallel. Another example. Again, pause the video and try this yourself. Find an equation of the plane that contains the points 1, 0, negative 1, 3, 1, 4, and 2, negative 2, 0. So it turns out that a plane is determined by 3 non-collinear points. If the 3 points lie on the same line, then that doesn't determine a unique plane. There are infinitely many planes satisfying that. So we do have to make sure that these 3 points do not lie on the same line, but that will be determined automatically when we take the cross product in a little while. Okay, so once again, to write an equation of a plane in point normal form, we need a point and we need a normal vector. So we have a few choices for points here. I'll use the point 1, 0, negative 1. Now, to get a normal vector, we're going to be taking a cross product. So we start by looking for two vectors that are in the plane that are not parallel to each other. And the cross product of those two vectors will be orthogonal to both of those vectors and therefore normal to the plane. So how do we get two such vectors? Well, we could just take pairs of points that are given here and subtract coordinate by coordinate. For example, if we take the first 2 points, we get the vector 3 minus 1 is 2, 1 minus 0 is 1, and 4 minus negative 1 is 4 plus 1, which is 5. And if we take the first and third points, we get 2 minus 1 is 1, negative 2 minus 0 is negative 2, and 0 minus negative 1 is 0 plus 1, which is 1. So taking the cross product, well, the I component, we get 1 minus negative 10, or 1 plus 10 is 11. For the j component, we have 5 minus 2 is 3. And for the k component, we have negative 4 minus 1 is negative 5. So we now have a point and a normal vector to the plane. We can go ahead and write an equation in point normal form. 11 times x minus 1 plus 3 times y minus 0, or just 3y, minus 5 times z minus negative 1, or z plus 1, is equal to 0. If we want the general form, we could just multiply everything out on the left to get 11x plus 3y minus 5z. And then we have negative 11 minus 5 adds up to negative 16. So we see that the d for the general form is negative 16. Okay, another example. Again, pause the video and try this yourself, and then resume the video and check your answer with mine. Determine whether the line x equals 3 plus 8t, y equals 4 plus 5t, z equals 3 minus t is parallel to the plane x minus 3y plus 5z equals 12. If not, find the point of intersection of the line with the plane. All right, so how do we determine if a line is parallel to a plane? Well, remember that the vector defining the line is parallel to the line, and the vector defining the plane is normal to the plane. So the line will be parallel to the plane if it's perpendicular or orthogonal to the normal vector defining the plane. So in other words, we need to check if the dot product of the vector defining the line and the vector defining the plane is 0. If it is 0, the line will be parallel to the plane. If it's not 0, the line will hit the plane. Okay, so let's take that dot product. The vector defining the line is 8, 5, negative 1, and the vector defining the plane is 1, negative 3, 5. The first vector there is parallel to the line. The second vector there is normal to the plane. When we take the dot product, we get 8 times 1 is 8, 5 times negative 3 is negative 15, negative 1 times 5 is negative 5. Add those up, and we get negative 12. That's not 0, so the two vectors are not orthogonal, and therefore the line is not parallel to the plane. So it follows that the line is going to intersect the plane. So how do we find the point of intersection? We'll start by finding the t value at which the point of intersection occurs. To do that, we'll replace x, y, and z in the equation of the plane by what they're equal to in terms of t from the parametric equations of the line. So in place of x, we put 3 plus 8t, and then we get minus 3 times y, which is 4 plus 5t, plus 5 times z, which is 3 minus t, equals 12. So when we add up all the constants, we have 3 minus 12 plus 15 is 6. And then we also have 8t minus 15t minus 5t is negative 12t. And so we have 6 minus 12t equals 12. Subtract the 6 to get negative 12t equals 6, and divide by negative 12 to get t equals negative 1/2. So that is the t value at which the line hits the plane. We can now figure out the point xyz by substituting that t value into each of the parametric equations. So we get the point -1, 3/2, 7/2. For example, we get -1 by taking x equal to 3 plus 8 times -1/2. We get 3/2 by taking y equals 4 plus 5 times -1/2. And we get 7/2 by taking z equals 3 minus -1/2, or 3 plus 1/2. Angle between planes. So here's a picture of two planes intersecting each other. There are actually two angles here. When we talk about the angle between planes, if we don't mention anything else, we will always mean the smaller of the two angles. In other words, the angle theta that is between 0 and pi over 2. Now, how do we find that angle? Well, the angle between two planes is the same as the angle between the two normal vectors. So we can find the cosine of the angle by taking the dot product of the two normal vectors divided by the product of the lengths. This follows from the formula we derived back in the section on dot product. Notice that I put the numerator in absolute values, right? The original formula didn't have absolute values, so why does this one? It's because if we leave out the absolute values, we may get either the smaller or the bigger angle. If we take the absolute value, we're guaranteed that we're taking cosine theta equal to a non-negative number, and therefore the angle will be in the first quadrant between 0 and pi over 2. Let's try an example. Again, pause the video, try this example yourself, and then resume the video to check your answer. Find the acute angle of intersection between the planes 2x minus 4y plus 4z equals 7 and 6x plus 2y minus 3z equals 2. Okay, so the cosine of theta is, on the top, we take the absolute value of the dot product of the two vectors. So 2 times 6 is 12, negative 4 times 2 is negative 8, 4 times negative 3 is negative 12. And on the bottom, we take the product of the two lengths. The first length is the square root of 4 plus 16 plus 16, which is root 36 or 6. And the second length is the square root of 36 plus 4 plus 9, which is the square root of 49 or 7. Okay, on the top, we get negative 8 in absolute values, which becomes 8. And on the bottom, we get 6 times 7, which is 42. That reduces to 4 over 21. Since the cosine of theta is 4 over 21, theta is the inverse cosine of 4 over 21. Okay, if we wanted to get a decimal approximation to this answer, we could put it in our calculator, but the question doesn't ask for an approximation, so we should always leave it in this form. This is fully simplified. Next, we want to talk about distances. The main theorem is that the distance d between a point P0 with coordinates x0, y0, and z0 and the plane ax plus by plus cz plus d equals 0, written in general form, is d equals the absolute value of ax0 plus by0 plus cz0 plus d over the square root of a squared plus b squared plus c squared. Now, this formula looks complicated upon first glance, but the idea is pretty simple. You can simply plug the given point in for x, y, and z into the equation of the plane, take the absolute value, and divide by the length of the normal vector defining the plane. So conceptually, it's not too hard to remember how to actually do this. Now, I'm going to give a derivation for this formula next. If you wish to skip that and go right to the examples, feel free. If you'd like to see the derivation, I will do that now. Let's start with an arbitrary plane and a point x0, y0, z0. The distance we're looking for is the perpendicular distance from the point to the plane, shown in red here. I'm going to draw the normal vector to the plane so that its initial point is in the plane and it passes through the point x0, y0, z0 if it can. Otherwise, it's on the line passing through that if it happens to be too short to actually hit the point. Let's take an arbitrary point xyz in the plane and draw the vector v whose initial point is xyz and whose terminal point is x0, y0, z0. And let's just draw a little line segment from xyz to the initial point of the normal vector to form a little triangle here. Notice that the distance we're looking for is the length of the projection of v onto the normal vector n. Now recall from the lesson on dot product that the formula for the projection of v onto a vector b is v dot b over the length of b times a unit vector in the direction of b, namely b over the length of b. So the length of the projection of v onto n is the absolute value of v dot n over the length of n. So let's compute that. The vector v is x0 minus x, y0 minus y, z0 minus z. The vector n is ABC. So when we take the dot product, we get x0 minus x times a plus y0 minus y times b plus z0 minus z times c. And the length of n is just the square root of a squared plus b squared plus c squared. Also note that I did have to put the numerator in absolute values. When we multiply everything out in the numerator, we get ax0 plus by0 plus cz0 minus ax minus by minus cz. Now notice if we look at the general form for the equation of the plane, ax plus by plus cz plus d equals 0, and we solve for d, we see that d is precisely equal to negative ax minus by minus cz. So we can make that substitution to get the formula we were looking for. Okay, it's time for some examples. Once again, pause the video before I go over this so you could try the example yourself. Find the distance between the point 2, negative 3, negative 1, and the plane 3x plus 2y minus z equals negative 2. Okay, we can just plug right into the formula, which basically means we're going to substitute 2, -3, -1 into the equation for that plane to get 3 times 2 plus 2 times -3 minus 1 times -1 plus 2. Remember, we have to bring that -2 over to the left-hand side. We take the absolute value of that and divide by the length of the normal vector, which is the square root of 3 squared plus 2 squared plus the square of -1, as we see there. And that comes out to 3 over the square root of 14. Okay, here's another example for you to try. Again, pause the video and try it yourself first. The planes x plus 2y minus 2z equals 3 and 2x plus 4y minus 4z equals 7 are parallel. Find the distance between them. Okay, we're given that the planes are parallel, but let's just check for ourselves to make sure. The vector defining the first plane is 1, 2, -2, and the vector defining the second plane is 2, 4, -4. Notice that those two vectors are parallel because we can multiply the first vector by 2 to get to the second vector. Or equivalently, 2 over 1 is 2, 4 over 2 is 2, and -4 over -2 is 2. So since all the quotients are equal, we know that the vectors are scalar multiples of each other. So since the normal vectors to those planes are parallel, the planes themselves are also parallel. So whenever we have two planes that are parallel, we could find the distance between them simply by taking a point, any point, on one of the planes, and then applying the distance formula with that point and the second plane. So let's find a point on the first plane. The easiest way to find a point on a plane is to set two of the coordinates equal to 0 and figure out what the third one is. So if we set y and z equal to 0, we see that x is 3. So the point 3, 0, 0 is in that plane. And now we can simply apply the distance formula with that point and the second plane to get, well, 2 times 3 plus 4 times 0 minus 4 times 0 minus 7. Don't forget to bring that 7 over to the left. Take the absolute value of that. And on the bottom, we have the length of the normal vector to the plane, which is the square root of 4 plus 16 plus 16. So on top, we get absolute 6 minus 7, which is the absolute value of -1 or 1. And on the bottom, we get the square root of 36, which is 6. So the answer is 1/6. All right, let's do one more example. This one's a little more challenging, so give it a shot. Pause the video, try it, and if you get stuck, no big deal. I'll go over it in just a second. The lines L1 and L2 are skew. Find the distance between them, and we're given two lines here. Okay, so we're given that they're skew. I'm not going to go ahead and check that because that would take a while, but using the techniques from the last lesson, you should be able to check that those lines are skew if you wanted to. How do we find the distance between two skew lines? Well, the idea is as follows. Given any line, there are infinitely many planes passing through that line. To see this, hold up one of your hands, think of your hand as the plane, and picture a line passing through the middle finger of your hand. Now, if you rotate your hand to the left and to the right, you can see that there are infinitely many planes that contain that line. Now, if you take two lines that are skew and you do the same thing, most of those planes, as you rotate them, will hit each other. But there's a unique pair of parallel planes that contain each of those lines. So what we're going to do is we're going to start with those two parallel planes and then apply a similar technique to what we did in the last example. So specifically, let's take planes P1 and P2 that are parallel, where L1 is in P1 and L2 is in P2. So to get the distance, we're going to need a point in the first plane, and we're going to need an equation of the second plane. It's easy to get a point in the first plane. Since P1 contains line L1, we could take any point on the line L1. And the easiest point to take is the one corresponding to t equals 0. So if we plug in a 0 for t into L1, we get x equals 1, y equals 5, z equals 1, and that gives us a point in plane P1. Next, we have to deal with the second plane, P2. We want to write an equation of this plane. So we're going to need a point in the plane and a normal vector to the plane. Let's start by getting the normal vector to the plane. How did I come up with these numbers here? Well, I simply used the vectors that define lines L1 and L2. Notice I put in 4, negative 4, 5 from L1 and 8, negative 3, 1 from L2. The reason this gives us a normal to the plane, and in fact, it gives us a normal vector to both planes P1 and P2 because they're parallel, is because if we're perpendicular to each of those vectors, then we're perpendicular to both of those skew lines and therefore perpendicular to each of those planes. Okay, so let's do this computation. The I component is negative 4 plus 15, which is 11. The J component is 40 minus 4, which is 36. And the K component is negative 12 plus 32, which is 20. So that gives us a normal vector to our plane. And for a point in the plane, we could do the same thing we did with the first plane. We could just take a point on the line L2. And the easiest point to take on the line L2 is by setting t equal to 0 to get the point 2, 4, 5. We can now write an equation of this plane in point normal form using the point and the normal vector we just found. So we have 11 times x minus 2 plus 36 times y minus 4 plus 20 times z minus 5 equals 0. Let's get this into general form by multiplying everything through to get 11x plus 36y plus 20z. And if we combine all those constants, we get minus 266 equals 0. Now we can find the distance by using the point 151 from the first plane and the equation of the second plane that we just found. And we go ahead and substitute. We get 11 times 1 plus 36 times 5 plus 20 times 1 minus 266 in absolute value over the length of the normal vector for the plane we just found, which is the square root of 11 squared plus 36 squared plus 20 squared. And when we do all those computations, we get 55 over the square root of 1,817.